Microsoft Fabric C/CD Deep Dive, how Git, deployment pipelines, APIs, and variable libraries transform analytics delivery. Hello and welcome. In this deep dive, we are going to explore Microsoft Fabric C/CD as a complete lifecycle management approach, not just a deployment feature. Fabric Lifecycle Management helps teams develop, test, release, and maintain analytics assets with more control and less manual risk. This matters because Fabric solutions often include notebooks, lakehouses, pipelines, semantic models, reports, warehouses, event streams, and configuration values that must move together safely. Without a structured C/CD process, teams can easily lose track of changes, override each other's work, or deploy content that points to the wrong environment. The goal is to make Fabric delivery repeatable, auditable, and reliable from development to production. Microsoft Fabric Lifecycle Management is built around two major ideas: integration and deployment. Integration is about connecting workspace content to Git so teams can version, review, branch, and recover changes. Deployment is about moving approved content through controlled environments such as development, test, and production. The documentation also highlights variable libraries, REST APIs, deployment rules, Git automation, and deployment orchestration patterns as key parts of the broader CI/CD picture. The best Fabric CI/CD design connects a development workspace to Git, then uses deployment pipelines, APIs, or automation tooling to promote content safely. This turns Fabric from a shared editing space into a managed engineering platform. Git integration is the foundation of source control in Fabric that lets developers connect a workspace to Azure DevOps, cloud repositories, GitHub cloud repositories, or supported GitHub Enterprise Cloud deployments and synchronize supported Fabric items with a Git folder. Once connected, Fabric shows whether each item has incoming changes, outgoing changes, conflicts, unsupported status, or synchronization updates pending. Developers can commit workspace changes into Git, update the workspace from Git, and use branches to isolate work. This is important because analytics artifacts become easier to review, restore, compare, and govern. Instead of relying on memory or manual copies, the team can use familiar pull requests and source control practices. Fabric Git integration works at the workspace level, which means supported items inside the connected workspace are exported to the Git repository as item folders and definition files. The workspace folder structure is preserved in Git, including subfolders up to supported limits. Each item includes system metadata such as type, display name, and logical ID values that Fabric uses to maintain item identity and synchronization consistency. This structure is powerful, but it also means teams should avoid casually editing generated files without understanding the impact. Unsupported items can exist in the workspace, but they are ignored by Git and cannot be committed or updated through Git integration. That behavior must be considered when designing CI/CD for mixed Fabric workloads. Teams should also remember that Git integration exports item definitions, not the underlying data stored inside Fabric workloads. A strong Fabric development model avoids direct changes in shared production workspaces. Developers should work either locally in tools such as Power BI Desktop or VS Code, or inside isolated Fabric workspaces created through the branch-out experience. In a local workflow, developers clone the repository, edit supported project files, commit changes, push a branch, and open a pull request. In a Fabric native workflow, a developer branches out to a separate workspace connected to a feature branch, makes changes in the service, then commits back to Git. Both patterns protect the shared team workspace from unfinished work. The key principle is simple. Development should be isolated, reviewed, and merged before release. Branch out is especially useful for Fabric items that must be edited directly inside the Fabric service. The branch out experience creates a new Git branch based on the latest sync commit and connects that branch to a separate workspace. Developers can then safely modify notebooks, pipelines, lakehouses, reports, semantic models, or other supported items without interfering with the shared team workspace. The documentation also describes selective branching, where only selected items are included in the branched workspace. This can reduce setup time, but dependencies must be selected carefully or the workspace may not function correctly. Before branching out, teams should commit anything they want to keep, because unsupported or unsaved content can be lost during the process. Since a workspace can connect to only one branch at a time, many organizations treat workspaces and branches as a one-to-one mapping for cleaner isolation and governance. Deployment pipelines provide the release management side of Fabric lifecycle management. A deployment pipeline can contain between 2 and 10 stages, with the most common model using development, test, and production environments. Content is developed in one stage, validated in the next, and released to production when ready. Deployment pipelines help teams compare stages, review deployment history, apply deployment rules, and promote content through a consistent release process. They are especially useful when organizations want structured stage-by-stage governance directly inside Fabric. The important distinction is that Git manages development history and collaboration, while deployment pipelines manage controlled promotion between environments. Teams should also remember that some deployment pipeline APIs currently focus primarily on Power BI items, while broader Fabric deployment automation increasingly relies on Fabric REST APIs and item definition APIs. The standard Fabric release pattern starts with a development workspace assigned to the development stage. The team builds or updates content there, usually with Git integration enabled for source control and collaboration. When the content is ready, it is deployed to the test stage, where reviewers validate functionality, refresh behavior, security settings, dependencies, and environment-specific configurations. After testing is complete and approvals are completed, the content is promoted to production for business consumption. Fabric can compare stages and show whether content is identical or different between environments. This makes release decisions more transparent because teams can clearly see what changed before promoting updates further. Many enterprise teams also combine deployment pipelines with Azure DevOps or GitHub Actions to automate approvals, testing, and deployment orchestration. Deployment rules solve one of the most common release challenges in analytics platforms. Each environment usually requires different configuration values. Development might use sample datasets, test might use validation systems, and production might connect to enterprise production sources. Deployment rules can adjust data sources, parameters, semantic model settings, or default Lakehouse references during deployment, depending on the supported item type. For example, semantic models support parameter and data source rules, while notebooks can use default Lakehouse configuration rules. Rules are configured in the target stage and are applied automatically during the next deployment into that stage. These capabilities reduce manual reconfiguration work and help prevent accidental production connection mistakes. However, teams must maintain role consistency carefully because changes to source parameters, unsupported query structures, or invalid connections can cause deployment failures. Variable libraries introduce a more centralized and scalable way to manage configuration across Fabric solutions. A variable library is a Fabric workspace item that stores reusable variables and values that other Fabric items can consume dynamically. Variables can represent simple values such as strings, numbers, booleans, or environment names, and they can also reference Fabric items such as lakehouses or warehouses. The same variable can maintain different values for development, test, and production environments, allowing deployments to resolve the correct configuration automatically based on context. This approach reduces duplicated configuration logic across notebooks, pipelines, semantic models, and other Fabric assets. For enterprise CI/CD processes, variable libraries improve consistency, simplify environment management, and make infrastructure and configuration behavior easier to standardize through deployment automation and lifecycle management workflows. The Microsoft Fabric documentation describes multiple CI/CD workflow patterns, and each one supports a different operating model and governance strategy. The first option is Git-based deployment, where development, test, and production each have their own dedicated branch and connected workspace. The second option extends that model by introducing build environments, where automation transforms or validates content before publishing to the target workspace. The third option uses Git primarily for development collaboration while relying on Fabric deployment pipelines to promote content across environments. Another model is designed for ISVs and large-scale organizations that manage deployments across many customer or tenant workspaces. In practice, many enterprises combine these patterns instead of adopting only one approach. The right architecture usually depends on branching strategy, automation maturity, compliance requirements, and the complexity of environment-specific configuration management. In the Git-based deployment model, Git becomes a single source of truth for the entire analytics platform. Each release stage has a corresponding branch, such as dev, test, and prod, and each branch feeds its matching Fabric workspace. When a pull request is merged into the development branch, automation updates the development workspace from Git. Once testing is complete, another pull request promotes the same approved changes into the test branch and eventually into the production branch. This creates strong traceability because every deployment can be tied back to commits, reviews, approvals, and merge history. The model works especially well for organizations using Git flow or strict release governance policies. However, it also requires disciplined branching practices, reliable automation, and careful coordination between development and release teams to avoid drift between environments. In the build environment deployment model, releases still originate from Git, but automation performs additional processing before publishing content into the target workspace. A pipeline can run validation tests, inspect definition files, replace environment-specific IDs, update connection references, adjust parameters, and prepare item definitions for deployment. This becomes important because Fabric item definitions often contain references such as workspace IDs, Lakehouse IDs, SQL endpoint IDs, semantic model bindings, or connection IDs that differ across environments. This approach is especially useful for organizations following trunk-based development strategies where a single main branch feeds multiple deployment stages. The trade-off is increased pipeline complexity because the deployment process now includes transformation logic in addition to publishing logic. However, the result is more reliable and repeatable deployment automation. For many enterprise teams, build environment workflows provide the best balance between centralized source control and flexible environment-specific deployment behavior. The fabric-cicd Python package is one of the major automation approaches highlighted in the documentation for deploying Fabric items programmatically. It allows pipelines or local scripts to publish Fabric item definitions from a Git repository into a target workspace using Fabric APIs. A typical Azure DevOps workflow installs Python, installs the fabric-cicd package, authenticates using a service principal, resolves the target workspace, and deploys selected Fabric item types. Item scoping is particularly important because organizations may want to deploy only notebooks, pipelines, lakehouses, semantic models, reports, or variable libraries in a given release. The deployment engine can also remove orphaned items that no longer exist in the repository. However, cleanup operations must be used carefully because deleting orphan content assumes the repository branch fully represents the intended workspace state. If teams deploy only partial content, automated cleanup could unintentionally remove valid production assets. A production-grade fabric-cicd deployment pipeline usually combines Azure DevOps variable groups, Azure Key Vault, service principal authentication, branch triggers, automated validation, and approval gates. Sensitive values such as tenant IDs, client secrets, and API credentials should be stored securely in Azure Key Vault and retrieved dynamically during execution. Less sensitive deployment settings such as workspace names, repository paths, deployment scopes, and environment mappings can be managed through Azure DevOps variable groups. Azure DevOps environments can also enforce approval workflows that pause deployment into test or production until authorized reviewers approve the release. Many teams derive deployment targets dynamically from branch names such as dev, test, or prod to reduce hard-coded configuration inside scripts. This creates a governed and repeatable promotion model that supports automation while still preserving enterprise release controls and operational oversight. Parameter files are another important component of automated Fabric deployment workflows. Files such as parameter, YAML are commonly used to replace development-specific UIDs and configuration values with test or production equivalents during deployment execution. Dynamic tokens can resolve values such as target workspace IDs, Lakehouse IDs, SQL endpoint IDs, connection references, or other environment-specific identifiers at runtime. This matters because notebooks, semantic models, pipelines, and other Fabric item definitions may contain hard-coded references created during development. Without replacement logic, a notebook promoted into test or production could accidentally continue pointing to development resources. Parameter replacement, therefore, becomes essential for safe environment isolation. Variable libraries and parameter files should be treated as complementary capabilities. where variable libraries centralize reusable configuration management and parameter replacement handles deployment time transformation of environment-specific identifiers and references. The bulk import item definitions API provides another powerful deployment mechanism for Microsoft Fabric CI/CD workflows. Instead of relying on a deployment library wrapper, a pipeline can directly read Fabric item definition files from a Git repository, encode them into the required payload structure, and submit them to Fabric's bulk import endpoint. The API can create new items or update existing items in place, while Fabric automatically manages dependency ordering during deployment. After the request is submitted, the pipeline monitors the associated long-running operation until deployment is completed successfully. This approach is especially useful for teams that want direct API-level control, custom deployment orchestration, or tighter integration with internal platform tooling. It also supports deployment patterns where a development workspace is connected to Git while downstream test or production workspaces remain disconnected from Git entirely. For many enterprise teams, this API-based model enables more controlled and standardized release automation across multiple environments. Fabric REST APIs extend CI/CD capabilities far beyond basic deployment automation. Git integration APIs can connect or disconnect workspaces, initialize Git synchronization, retrieve Git status, commit workspace changes, update workspaces from Git, and monitor long-running operations. Deployment pipeline APIs can list pipelines, retrieve stage information, assign workspaces to stages, deploy stage content, manage role assignments, and track deployment history and operation status. These APIs make it possible to integrate Microsoft Fabric with Azure DevOps pipelines, GitHub Actions workflows, enterprise schedulers, internal developer platforms, and automated governance systems. However, organizations must understand that capabilities differ between Fabric APIs and the older Power BI deployment pipeline APIs. Some deployment pipeline APIs still focus primarily on Power BI workloads, while broader Fabric deployment scenarios increasingly depend on Fabric REST APIs and item definition APIs. Teams should carefully validate API support, item compatibility, authentication requirements, and deployment limitations before standardizing on an enterprise automation architecture. Service principal authentication is a foundational requirement for enterprise-grade Fabric CI/CD automation. Production deployment pipelines should never depend on an individual user account because user credentials expire, permissions change, employees leave organizations, and operational ownership becomes difficult to govern. A properly configured service principal can authenticate securely to Fabric APIs, Azure DevOps, Git repositories, and supporting automation services. The service principal must be granted the necessary permissions for Fabric workspaces, deployment pipelines, repositories, and Git connections. Fabric administrators may also need to enable tenant settings that allow service principals to use Fabric APIs. Secrets and credentials should always be stored securely using Azure Key Vault or equivalent enterprise secret management platforms with regular credential rotation policies enforced automatically. This approach creates more stable, auditable, scalable, and production-ready deployment automation across analytics environments. Permissions and governance planning are critical because Fabric workspace permissions, Git repository permissions, deployment pipeline permissions, and API permissions all operate independently. Workspace administrators are generally required to connect or disconnect Git repositories and manage workspace-level connection settings. Contributors can commit or update content only when they have both the required workspace permissions and the appropriate Git repository access. Deployments between stages require proper access to both source and target environments, especially when content already exists in downstream stages. Deployment rules and configuration changes may additionally require ownership or elevated rights on the target item. Organizations should clearly define who can develop, review, approve, deploy, administer, and access production content before the first release pipeline is implemented. In many enterprise environments, successful CI/CD governance depends more on thoughtful permission architecture and operational controls than on the deployment scripts themselves. Conflict resolution is a normal part of collaborative Git workflows in Microsoft Fabric. Conflicts occur when the same item is modified both in the Fabric workspace and in the connected remote Git branch before synchronization happens. Fabric provides options to either accept incoming Git changes or preserve the current workspace version, depending on the synchronization state and conflict type. Teams can also resolve conflicts directly in Git by creating branches, committing workspace changes, merging carefully, and then synchronizing the resolved version back into Fabric. The compare code changes capability is especially valuable because it exposes file level differences before commit, update, undo, or conflict resolution operations occur. This visibility helps teams understand exactly what changed inside item definition files, metadata structures, parameters, and configuration references, instead of simply seeing that an item was modified. Strong conflict management practices become increasingly important as multiple developers collaborate across notebooks, semantic models, pipelines, reports, and other shared Fabric assets. Logical IDs are one of the most important identity management concepts in Microsoft Fabric CI/CD. A logical ID connects a Fabric item in a workspace to its representation in Git and preserves that relationship across synchronization and deployment operations. If two items share the same display name and item type but have different logical IDs, Fabric can detect a metadata conflict because it treats them as separate identities internally. In some scenarios, overriding workspace metadata with the Git version can realign the environment, but doing so may also break downstream dependencies, automations, deployment mappings, or item references that relied on the original identity. Keeping the workspace version instead may require updating Git definitions to match the workspace logical IDs or renaming conflicting items. Teams should treat logical IDs as stable identity keys and avoid modifying them manually unless they fully understand the implications. Logical ID consistency is essential for reliable synchronization, dependency tracking, and long-term lifecycle management stability. Deployment failures in Microsoft Fabric often originate from dependency issues, invalid deployment rules, unsupported item behavior, or mismatched environment configuration. For example, a deployment rule may fail if a semantic model parameter was removed, renamed, or reordered after the rule was created. Data source rules can also fail when semantic models use unsupported connection patterns, parameterized sources, or unsupported query structures. Synchronization and deployment operations may additionally fail when dependent items were deleted, circular dependencies exist, item definitions are invalid, unsupported items still reference supported items, or workspace configuration no longer matches the repository structure. In some cases, updates can fail partway through execution, leaving the workspace in a partially synchronized state. The safest recovery approach is usually to identify the failing item or dependency, correct the issue in the Git source, validate the configuration carefully, and then rerun the update or deployment process. Strong dependency management and small incremental changes significantly reduce these types of operational failures. Microsoft Fabric CI/CD includes important operational limits that should influence workspace architecture and deployment design decisions from the beginning of a project. Some Fabric item types are still supported only in preview, while unsupported items are ignored during Git synchronization instead of being deployed or versioned. Fabric also enforces workspace item count limits, branch name limits, file path length limits, file size limits, and folder depth restrictions. Large enterprise environments may therefore need to be separated by domain, business unit, workload type, ownership boundary, or release cadence to remain maintainable. Additional restrictions can apply to scenarios involving sensitivity labels, B2B collaboration, sovereign cloud environments, Git submodules, conditional access policies, or certain GitHub enterprise configurations. Deployment pipelines also include API limits, stage limits, and workload-specific support constraints, with some capabilities still focused mainly on Power BI items. The most sustainable long-term strategy is usually to design smaller, modular, clearly governed workspaces before the environment grows too large and operationally complex. Security architecture and network governance are also critical components of Microsoft Fabric lifecycle management. Workspace-level security controls can restrict inbound and outbound access, and outbound protection policies may directly affect whether Git synchronization and deployment operations are allowed. This matters because Git integration moves Fabric item definitions between the workspace boundary and external Git repositories such as Azure DevOps or GitHub. Administrators may therefore need to explicitly allow Git connectivity for secured workspaces while also monitoring synchronization activity through audit logging and security controls. Certain workspace inbound and outbound protection configurations currently limit or prevent deployment pipeline functionality altogether. In regulated environments, CA/CD architecture must therefore include security design, identity management, network segmentation, auditability, and governance planning alongside repository and automation design. Effective enterprise automation requires balancing developer productivity with strong compliance, security, and operational control requirements. A practical end-to-end Fabric C/CD process starts with workspace and repository planning. First, define development, test, and production workspaces, decide which Fabric items belong together, and choose a repository folder structure that supports clean ownership and release boundaries. Second, connect the development workspace to Git and confirm that supported items synchronize cleanly without conflicts, unsupported dependencies, or invalid folder structures. Third, establish branch policies, pull request reviews, and developer isolation through local tools or branch out workspaces. Fourth, decide whether promotion will happen through Git-based deployment pipelines, Fabric C, bulk import item definitions, APIs, or a hybrid model. Fifth, configure environment-specific values using deployment rules, variable libraries, parameter files, or scripted replacement logic. Finally, add approval gates, service principal authentication, deployment monitoring, rollback procedures, and production access controls before releasing business-critical content. The strongest Fabric C/CD implementations treat analytics delivery like modern software delivery, while still respecting Fabric's unique workspace-based operating model. Git provides version history, branching, collaboration, pull request review, and recovery. Deployment pipelines provide visual stage promotion, environment comparison, deployment history, and deployment rules. Variable libraries reduce duplicated environment configuration and make values easier to reuse across Fabric items. Fabric-CICD and bulk import item definitions APIs enable automated, repeatable deployment from repository-based item definitions. Service principals, Azure Key Vault, approval gates, workspace permissions, and Git permissions provide the governance foundation required for enterprise release management. When these capabilities work together, Fabric teams can release analytics assets faster while reducing manual risk and protecting production stability. Thank you for taking the time to explore this topic, and I hope this deep dive helped you understand how to build reliable CR/CD for Microsoft Fabric.